Hi! In this video, I'll be talking about the limiting behavior of functions with multiple variables. So this is really a generalization and extension of the idea of limits from single variable functions to now multivariable functions. And once you're able to understand it in two variables, then you'll be able to understand it in n variables. So let's begin. We define the limit of a function of two variables as follows. If given an epsilon, there exists a delta such that whenever the point xy is close to AB that you want, delta close, then fxy minus L is less than epsilon. Informally, this means that fxy gets closer to L as xy gets closer to AB. So if you have watched the video on analysis metric spaces, you will understand that we're just using the general definition of a metric to define this limit. And so really it comes as no surprise that we have a disk and xy is a point in the disk center about AB and the radius is delta. Then the function will be within epsilon distance from L. And some remarks to note is that in real numbers, you can get to a point in only two ways. You either go from the left or you go from the right. And so we say that the limit exists if and only if the left and right hand limits are equal to one another and existing. But when you are dealing with multiple variables in higher dimensions, now you can go to the point AB in infinitely many ways because you can go from any path. And so to show that a limit exists, it is not good enough to show two paths are the same limit and they equal. You have to make sure that all the continuous paths are of the same limit and are equal. So we will take a look at some examples and then you'll get to understand how we use limits and how we play around with limits. So firstly, we of course want to show that this limit equals to 0. Why 0? That's like a given in the question, but usually when you're doing an open problem, it could be just like you guessed it to be 0 through other methods. And really you want it to be 0 because you understand that this function will go to 0 faster than the bottom, so you think that it will go to 0. So you let it equal to 0, the limit, and then you prove that it is 0. So now you're given epsilon, you want this inequality to hold true. So when you find a suitable delta, well, you recognize that this modulus of 3x squared y over x squared plus y squared can be written as being less than or equal to 3y because x squared plus x squared over y squared is less than 1. And so this part is fractional, so it's less than 3y. And we know that the 3 less than mod y is 3 square root y squared. And really, if you add an x squared, then it will be larger already. So that's why you have this inequality. And so we know now we have a square root x squared plus y squared here, and this is less than delta. So we just need to choose a delta equal to epsilon over 3. And when this occurs, this is less than epsilon over 3 times 3, which equals to epsilon. So this portion will be less than epsilon. And by the definition, it means that the limit equals to 0 as a result. So that's how we want to show that the limit exists by using the definition. If we want to show the limit does not exist, we have to find two paths such that the limit does not equal to each other. For example, in this question, we want to travel along the y equals to 0 line as x approaches 0. So we are keeping y equals to 0 and varying x. And we show that the limit equals to 1. But now when we approach it along the y-axis, you can show that the limit equals to minus 1. And so when you go along the x-axis and when you go along the y-axis, there are two different paths and their limits are not the same. And so the original limit that we want does not exist. Now, for this example, we want to show that the limit of xy over x squared plus y squared does not exist. Again, we will try our approach first of going along the x-axis, and we show that it does equals to 0. And as we travel along the y-axis, it equals to 0 as well. So this might confirm to you, this might suggest to you that it equals to 0. But however, you cannot say that it does equals to 0 because you have not checked all paths. So we cannot conclude anything as the limit may or may not exist yet. So now we try the path y equals to x. And using this path, we can actually show that the limit value of when you're traveling along y equals to x is half instead. And as a result of this means this path has a different limiting value compared to the others earlier. And so the limit of xy over x squared plus y squared does not exist. And so you can see how even though we are able to find two paths that equals to the same limit, the limit might not still exist because as long as you can find another path, and there are infinitely many paths as such, the limit will not exist. So this gives us a reason and a motivation to find certain properties of limits so that we can easily calculate the limiting value of a function. So for example, we have two functions that limits exist. Then you have all the properties that you had in your one variable case, such as your addition, your scalar multiplication, your product rules, and so on. And these properties of limits was already proven in our analysis video, so I'll leave it to you to check it out. But now with this slew of properties, you are able to use it to easily determine what a limit should be or should not be. And if you know that these two exist, then you know that limit must be this. Another use that we often associate to finding limits is known as the squeeze theorem. And the squeeze theorem states in two variable case that if it is exactly the same as in your one variable. If your function is now bounded between two other functions, then if these two functions g and h have limiting values of L as xy approaches ab, then you know that your middle function is squeezed between it will have a limit value of L as well. And the proof of the squeeze theorem is in my analysis series, so check it out. We shall focus more on the calculative part since we are really wanting to use the ideas of limits to help us solve questions, which is calculus. So you want to calculate the limit of this function, and you can really see that in our earlier example we have shown that it equals to 0 using the definition. But now we shall make use of the squeeze theorem to easily show it. Because we know this function now is bounded by 3 times mod y. But we know 3 mod y can be expanded out into minus 3y and 3y because this here is a modular sign. And so, because both of these equals to 0 as y goes to 0, then this limit must be 0. So you can see how this helps us find an easier method to finding the limit of a function. And lastly, the notion of continuity is just that as the limiting value of f as xy approaches ab is fab. And you get the same ideas as you were in your one variable case where two continuous functions added together is still continuous, the product is still continuous, as well as the quotient. Also, continuity and composition respects each other. When you compose two continuous functions, you are still continuous. And of course, you can generalize this to any function in Rn and not just two variables. And because of that, we get polynomials, trigonometric functions, and rational functions to be continuous. So now that you have the notion of limits for multivariable, you can see that you just need to change a bit from the one single variable case, and now you can extend it on to higher dimensions. And with that, I've come to the end of this video. I hope you have enjoyed it. If you have any questions, you can leave it in the comment sections down below. Bye!